Hey there, and welcome. We're going to talk about something that's literally all around you, pushing on you right now, but you probably don't even notice it. It's the reason a sharp knife works, how a massive dam holds back a lake, and even why your ears pop when you're in an airplane. We're going to dive into this hidden force called pressure. And, believe it or not, it all kicks off with a really simple question.
So, have you ever really thought about this? A thumbtack. Why is it so ridiculously easy to push the sharp end into a corkboard with your thumb, but you would never even dream of trying it the other way around? I mean, that would hurt. Well, the answer to that little puzzle is the key to understanding this whole thing. It's all about the physics of pressure.
Okay, so first things first, we have to get one thing clear right off the bat. A push, or what scientists would call a force, is not the same thing as pressure. They are definitely related, for sure, but that little difference between them, it's absolutely crucial. It changes, well, everything.
All right, try this with me right now. Just press the fingertips of one hand against the other. What do you feel? I mean, you could say you feel a force, right? A push. But you could also say you feel pressure. And honestly, you'd be right both times. So, what is the difference? How do these two ideas work together? Let's break it down.
This helps us see what's going on. So imagine you've got this cube. Its weight, the force of gravity just pulling it straight down, is 500 newtons. That whole 500 Newton force is pushing down on whatever surface it's sitting on. But here's the key. That force isn't just a single point. It's spread out over the whole bottom of the cube.
And that brings us to the big idea for today, this simple formula. See, pressure is just how much force you can cram into a specific area. It's the concentration of the push. So it's not just about how hard you're pushing, it's about how focused that push is. Okay, now this is where it all clicks into place. Look at this. We've got the exact same block in both pictures. Same weight, same stuff, which means it's pushing down with the exact same force. But look at the difference. On the left, it's standing on its end. All that force is focused on a tiny little area, which creates a ton of pressure. But on the right, it's lying on its side, spreading that same force over a much bigger area. The result? Way less pressure. See? Same force, totally different pressure.
So, the secret ingredient, the magic variable here, is the area. And once you get that, you start seeing it everywhere. You realize how we humans have become total masters at playing with area to get what we want.
I mean, think about walking in deep snow with just your boots on. Every step, you sink right in, right? It's exhausting. But then you strap on a pair of skis or snowshoes, and suddenly you're gliding right on top. What changed? Not you. It's still the same you, the same weight, the same downward force. The only thing that changed is that the skis spread your weight over a huge area. That drops the pressure way down so you don't break through the snow.
And that's our first big rule of thumb. If you want less pressure, you just spread out the force. A bigger area equals less pressure. It's that simple, and it's incredibly powerful.
Okay, but what if you want to do the opposite? What if you want to create insane amounts of pressure? Well, you just flip the script. You make the area tiny. A sharp knife has a microscopic cutting edge. It takes the little bit of force from your hand and concentrates it all onto that one tiny line, creating enough pressure to slice right through an onion. Same idea with the spikes on a track shoe. They focus the runner's entire weight onto a few tiny points, digging into the track for amazing grip. And there's our second rule, the other side of the coin. To get more pressure, you focus the force on a smaller area. Less area, more pressure. This is exactly why needles, nails, and, yep, our friend the thumbtack all have sharp points.
All right, so this whole pressure thing isn't just for solid objects. It's a huge deal in liquids, too. I'm talking about everything from the deepest part of the ocean to the water in your pipes. But with liquids, the rules change just a little bit.
This old-school experiment shows it perfectly. Just look at the streams of water. See how the one from the bottom hole is shooting out the farthest and the fastest? Why is that? Well, it's because that water at the bottom has the weight of all the other water above it pushing down on it. So in a liquid, it's simple. The deeper you go, the more pressure you get.
Now let's take that little cylinder and scale it way, way up to something massive, like a hydroelectric dam. Engineers who build these things know exactly what's going on. They know the pressure at the bottom of that huge lake is absolutely immense, and that is precisely why dams are built to be incredibly thick and strong at the bottom, and they can be much thinner up at the top. It's all designed to handle that incredible deep water pressure.
Things get even crazier when you trap a liquid inside something. This is cool. If you push on a liquid in a sealed container, that pressure doesn't just stay in one spot. It gets transmitted equally to every single part of the liquid and the container.
So a little push on that small piston on the left creates pressure that zips through the fluid and pushes up on everything, including that much bigger piston on the right. And this is where the magic happens. We call this a hydraulic system, but really it's a force multiplier. Because that piston on the right has a much bigger area, the same pressure creates a much, much bigger upward force. It's how a mechanic can use a little bit of effort on one end to generate enough force on the other end to lift an entire car. It's amazing.
Okay, so we've talked solids, we've talked liquids. What's left? Gases. And this might blow your mind a little bit. But right now, all of us are living at the bottom of a massive ocean. It's about 1,000 kilometers deep, and it's an ocean of air. And all that air has weight, and it's pushing down on us constantly.
The sheer weight of that column of air above you creates a pressure of about 100,000 newtons on every square meter of your body. To put that in perspective, that's like having 10 tons sitting on you. So, why aren't we all squished into pancakes? Well, it's because the pressure inside our bodies is pushing out with the exact same force. It's a perfect balancing act.
And you have definitely felt this balance get thrown off. You know when you drive up a mountain or take off in an airplane and your ears feel weird? That's because the air pressure outside is getting lower, but the pressure inside your head is still high. That extra pressure inside pushes on your eardrum. Then you swallow or yarn, and this little tube called the eustachian tube opens up, lets a little air out, and pop! The pressure's equal again. That's what that pop is.
So what would happen if you just took away that inside pressure? Well, this is what happens. In this famous demonstration, a vacuum pump sucks all the air out from inside the sturdy metal can. And without that air inside pushing back, the huge invisible pressure of the atmosphere on the outside has nothing to fight against, and it just crushes the can instantly. That's the real power of the air we're swimming in every day. So there you have it. From the tip of a thumbtack to the massive weight of our atmosphere, pressure is this incredible, hidden force that shapes almost everything. It's fundamental to our world, and we've gotten really, really good at using it. So the only question left is, now that you know the secret, where are you going to see it next?